Hey, welcome to The Explainer. Today, we're going to go on this incredible journey, starting with just a handful of sand and ending up with the supercomputers that power modern AI.
So how do you build an AI from a grain of sand? I mean, it sounds completely impossible, right? Like some kind of magic trick. But it's honestly one of the greatest technological stories ever told. We're going to uncover that story layer by incredible layer. Let's get into it.
Okay, so every journey has to start somewhere. And for the entire digital world, that starting point is sand. But, not just any sand you'd find on the beach. We're talking about super purified quartz, which gives us the one essential element for literally everything that follows, silicon.
This is really where the magic starts. See, a normal wire, it's just on or off, simple. But a semiconductor, that's totally different. Think of it like a finely tuned valve or a dimmer switch. We can control exactly how much electricity gets through. And that ability, that precise control, is the secret ingredient for all of modern computing.
And this chart just lays it out perfectly, doesn't it? A conductor like copper, that's a wide-open faucet. Electricity just gushes through. An insulator, like rubber, that's a completely blocked pipe. Nothing gets past. But the semiconductor? That's our adjustable faucet. It's the dimmer switch. It's the control we've been looking for.
All right, so we've got our magic material, silicon. What's next? Well, now we have to shape it into something useful. The very first digital brick. And this one invention, you could argue it's the most important one of the entire 20th century.
And here it is, the MOSFET transistor. You can think of it as a tiny, tiny electronically controlled gate. This thing is the fundamental atom of the digital world. I mean, billions, literally billions of these microscopic switches are working together right now to power everything from the watch on your wrist to the massive data centers that run AI. Every single bit of information is flowing through switches just like this. So how does this little gate actually work? It's surprisingly simple, really. First, you apply a tiny little voltage to what's called the gate. That signal creates a channel. It's like it opens a door. And once that door is open, a much larger current can flow right on through. Take that tiny voltage away, the door slams shut. That's it. It's a simple, elegant, and unbelievably fast electronic switch. Okay, so once this digital brick was invented, the game was on. The next 50 years or so became this all-out race to just shrink it down. Smaller, faster, cheaper. This relentless push was famously captured by Moore's Law, the idea that we could basically double the number of transistors on a chip every 2 years. And you know what? For decades, we actually did it.
Which brings us to today. This number, 3 nanometers, that represents the absolute cutting edge, 3 nm. To give you some context for just how small that is, a single human hair is about 100,000 nanometers wide. We are building structures that are literally smaller than a virus.
Yeah, it's a scale that is almost impossible to wrap your head around. We're talking about fitting over 100 million of these things on the head of a pin. At this level, we are literally manipulating matter, pushing individual atoms into place to build these switches. The engineering that goes into this it's nothing short of miraculous, really.
And this just shows you the incredible ingenuity it took to get here. Because as these transistors got smaller and smaller, they started to leak current, kind of like a dripping faucet you can't quite turn off. So what was the solution? The FinFET design. It's genius. Instead of a flat gate on top, they built a 3D fin that sticks up, and then they wrap the gate around it. It gives them so much more control. It's like gripping that faucet handle from 3 sides instead of just one. But then, how in the world do you print something that small? Well, you need a very special kind of light. It's called extreme ultraviolet, or EUV lithography. It uses this incredibly short wavelength light to etch these impossibly tiny patterns onto the silicon.
So, okay, we have billions of these microscopic switches. But, a giant pile of bricks doesn't just become a skyscraper. The real genius is in the architecture. It's all about how we arrange these billions of transistors to create a brain that's specifically designed for artificial intelligence.
And this table breaks down the different approaches perfectly. Think of a CPU, the processor in your laptop, as like a brilliant professor. It's amazing at solving one very complex problem at a time, step by step. A GPU, on the other hand, is like an army of students. You give them a huge problem and each one handles a tiny, simple piece of it all at once. But an AI accelerator, that's a completely different beast. It's a purpose-built factory. It has assembly lines designed to do one specific type of math, the matrix multiplication that AI is built on, and it does it at absolutely blistering speeds.
But we are hitting a wall, a physical wall.
We just can't shrink these silicon transistors much further before the very weird laws of quantum physics start messing things up. So that leads to probably the biggest question in all of technology right now. If our digital building blocks can't get any smaller, what do we build with next?
And here's some of the leading contenders for what comes after silicon. You've got materials like gallium nitride or GaN. It can handle more power and switch way faster than silicon, which makes everything more efficient. And then you have these mind-bending 2D materials like graphene. We're talking about a sheet of carbon that is literally one single atom thick. These could lead to circuits that are fundamentally faster and waste way less energy than anything we can even dream of with silicon today. And that brings us to the most exciting question of all, doesn't it? Our journey started with something as common as sand. And from that, we built machines that can think, that can create art, that can reason. But now the very foundation of that entire journey, the material itself, is about to change. So think about this. We built thinking machines from sand. What in the world are we going to build with these new materials?